Question involving waves in a nutshell. So we're going to talk about is how to calculate wavelength, frequency, energy, and what makes a wave a wave. So let's start off. We're going to first talk about the electromagnetic spectrum. So EM waves, or electromagnetic spectrum, is basically all the different possible waves that we're commonly made aware of. So you have gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, radio frequency. In total, these are all the different possible waves we're going to be dealing with. And what I want you to note is a couple of details about this. The smaller the wavelength, the bigger the frequency. So you can see the wavelength here is 10 to the negative 11. Notice the frequency that corresponds, that's a bigger number. So before we get into what the numeric values really represent, the only thing I want you to pay attention to is the fact that this is a lot smaller number than 10 to the third is, but yet look at the frequency that corresponds, it's a much larger number. So we refer to it as an inverse relationship. As the wavelength goes up, frequency goes down, and vice versa. I also want you to pay attention to the visible region, the colors. So what you know about colors is that everything has a different color, and it's basically based on the fact that light hits the object, and what you may or may not be aware of is that what you are seeing is what the color that's reflected back at you. So for example, if you see a red shirt, that means all these colors are absorbed from blue all the way to orange, except the color you're seeing, which is red. So color is basically a product of light, which is energy, that's EM waves, hitting the object and causing it to reflect back the color you're seeing and absorb all the rest. So you may be asking yourself, well, what about black? That's an absence of color. No, what's happening with black is absorbing all the colors. So you're not reflecting anything back, and that's why you're seeing black. Same thing with white. White isn't absorbing anything. Everything is reflected back. So what I want you to understand about colors from here on out is it's basically a product of energy hitting something, causing the atoms, the electrons inside the atom to jump to another shell, jump back down and produce colors. So in the case of red, what's happening is that the atoms that make up the dye in your shirt is being excited, which is a simple way of saying it's being forced to jump from, let's say, the second shell to the third shell. And when it comes back down, like it has to, anything that goes up must come down, it produces the colors you're going to see, which is red. That's what color is created by. So I'm going to talk about these waves and how to calculate this throughout this section. So first off, electrons and light. Creation of light and color. Color is the result of electrons moving between shells, like I mentioned. And really what it is that, let's say you have a shell here. Let's say it's the second shell. This is the third shell. This electron, we're represented with this little funny looking symbol, jumps up because you put energy in. Let's say you put a fire into it. Maybe you put electricity into it. Whatever you did, you cause it to jump to another shell. It can't stay here. So when it comes back down, it releases that energy you put into it. And what you're going to see is color. The further the electron travels, the more energetic the color. In case you didn't know, here's a color spectrum. The most energetic color is violet. The least energetic is red. That's why you see a lot of red lasers. You never see a violet laser. Violet laser is way more deadly than a red laser is. And you probably all heard of the fact that, if a red laser hits your eye, it's damaging, but your blink speed is enough to block it. That's still not a good idea to point lasers at anybody, but it's not nearly as deadly as violet is. Violet is extremely deadly. There's an inverse relationship between energy and wavelength. So which one of these do you think has the longest wavelength? Well, whichever one's the least energetic, which is red. So this is a long wavelength. We'll represent wavelength with this funny little symbol. It's called lambda. And it's going to have a low frequency, which we're going to represent by the symbol V. Violet, on the other hand, is going to be the opposite, because the most energetic color is going to have a short wavelength. It's going to have a high frequency. So that's how you could tell what's the more dangerous colors. So you could actually look at a color and kind of hypothesize, okay, it's going to have a short wavelength or high wavelength based on knowing your color spectrum. So color and light waves are inversely related. And as we said, there's two components we're going to touch on first, which is wavelength and frequency. So let's get into it. So wavelength is represented by the symbol lambda. That's that fun looking upside down V. It actually looks like a Y. It's got the little tail, right? So what is a wavelength? The wavelength is the distance between two tops of the waves, or the two bottoms. The tops are called crests. The bottoms are called troughs. So the distance between two crests or two troughs is what wavelength really is. Frequency, on the other hand, represented by symbol V, is the number of waves that pass a given point per second. So what does that mean? Well, things that have really long wavelengths are going to pass less times through a specific point. Let's say that I make this the point right here. Longer wavelengths would take longer to get past this point, but short wavelengths pass more. There's more waves they'll pass per second compared to a long wavelength. The units for frequency is either hertz or seconds. They're the same thing. Hertz and s to the negative 1 is the same thing. And in case you're wondering what the heck is s to the negative 1, it's just basically 1 over s. Whenever they have a letter or anything to negative 1 power, like let's say I say 10 to the negative 1, what I'm really saying is 1/10, in case you didn't know. So in this situation, it's 1 over s. And that's the same thing as a hertz. So they're synonymous. We need to know that. All right, difference between frequency and wavelength. So frequency and wavelength are inversely related. Formula for calculating it is this. This is a very important formula. This tells you that when you multiply the wavelength times the frequency, it equals to the speed of light. That's what c is. C is the speed of light. And you're asking, what's the speed of light? This is the speed of light. Now, something you need to be aware of is that this is a constant. This is going to be given to you. So what is this formula really used for? To figure out the wavelength when you have the frequency and figure out the frequency when you have the wavelength. So it's allowing you to calculate between the two of them. That's important. If you're aware of what that calculation is used for, let's talk about this little diagram. So the question in here is that which one of these two is more deadly, the red laser or the violet laser? So remember, long wavelength means short frequency, and short frequency means long wavelength, or small frequency equals large wavelength, however you want to look at it. So this one has a longer wavelength than this, right? So which one of these has a higher frequency? The answer is obviously this one, because this has a long wavelength, and this should have a higher frequency because it has a short wavelength. And that's what this is stipulating. The other thing you want to be aware of is the higher the frequency, the more energy. So when this wave hits you, it may hurt a little bit, or you won't even feel it's red. But let's say hypothetically you could feel both of these lasers. The red laser you'll feel a little bit. The violet you would feel really a lot. It's like having a small little having a small little wave hit you versus having a gigantic wave hit you. The amount of energy that's transferred in that small wave is almost nothing, but the other wave will create a lot more damage because it's going to have more force. And things that have short frequencies have a lot of energy stored within them. So it's an opposite relationship. And remember, we already talked about rho G bib and which one's more energetic. So hopefully that's beginning to make a little bit of sense. All right, let's talk about the math. So what is the frequency of a yellow light that has a wavelength of 589 nanometers? So this is the actual wavelength of yellow light. In case you didn't know, the wavelengths for color is basically your rho G bib. It's somewhere between 400 and about 700, give or take a few nanometers. These are all nanometers. And nanometers is a very, very small value, very small unit. And that's important to note because we need to be able to convert between nanometers and meters, and here's why. Your C is 3.0 times 10 to the 8 meters per second. Now, the way the math works for this, if I'm trying to figure out the frequency, the meters cancel out with the unit for meters, whatever unit you have. You're left with s to negative 1, or 1 over s, which is basically your frequency. I'm going to show you how that works out in a second for those who are looking at like, what the heck are you talking about? So what we're going to do is convert the units for nanometers into meters. And how we do that is very simple. All you have to do is just put 10 to the negative 9 at the end of it. That's all you got to do. I'm going to show you how that works mathematically. So we have 189 nanometers. Now we've talked about T-charts. And what we're saying here is this 1 times 10 to negative 9 meters is equal to 1 nanometer. Notice the units cancel out. You're left with 589 times 10 to the negative 9. Now we could put a scientific notation, but we don't want to, so we're not going to. Because it's not your final answer. It's just part of the values you need to get your final answer. So now we're going to take the equation for speed of light, and we're going to isolate our variable. This is a very important step. if you're going to try to solve for frequency, you need to have the V by itself. And for those like, how do you get by yourself? Really easy. Whatever's on the same side. So in this situation, we're just going to divide out the wavelength. So when we do that, the wavelength goes away on this side and you get C over wavelength on this side. So that's for frequency. And if in case you're wondering, what is it for wavelength? Same thing, just C over V instead. Those are your only two options. It's either one or the variable isolated. We could do the math. Please don't get in the habit of trying to do the math with the formula in the original form, this thing. Please get the letter by itself before you plug in numbers. It just makes it a lot easier. So let's get into this part. Okay, so remember what I said about those units things? So if you had nanometers up here, nanometers divided by meters gives you nanometers over meters. It does not cancel out the unit. So that's why we have to have the same unit for both the distance or the wavelength and this meters per second, which is the speed of light. So the way we do this, once again, is just take whatever number they give us in nanometers, put 10 to the negative 9 at the end of it. That's really that simple. And then just plug and chug into the formula. So here, look what happens to meters. What are you left with? 1 over S, basically, right? And that's S to the negative 1. So the math now is 3 divided by 589, and then times 10 to the 8 over 10 to the negative 9. So if you take your calculator out, the best way to do this, if you're not used to using the math on your calculator, or using a calculator for doing exponents, is just take the 3 divided by 589 in your calculator. So you end up with 0.00509 times 10, and then 8 minus a minus 9, which becomes 10 to the 17th, right? So you look at this, like, wait, that's not even the same number. It's S to the negative 1. Yeah, it is, because here's what you're going to do. You're going to move decimal point 1, 2, 3 times. Why 3 times? Because you can only have one number to left of the decimal point. This is when the scientific notation stuff comes in handy. Because I moved the 3 to the right, your exponent goes down by 3. So you go from 17 to 14. S to the negative 1. So that's how you can calculate it. For those that want to do it in your calculator, I'm going to show you how to do that real quick. So let's get out of there. We're going to open up our calculator. So I'm going to show you TI. You can actually download this yourself. TI-83, you can download it onto your computer if you want to. So let's take a look at this original calculation. We're going to use the TI to calculate it. So watch how I do it. 3. Most calculators have this thing called the EE button. That tells your calculator times 10 to that power. So rather write 3 times 10 to the 8th, what I'm going to do is go 3E 8. That's the same thing as this. So 3E to the 8th is the same thing as writing 3 times 10 to the 8th. That's what your calculator interprets. If you try to go 3 times 10 to the 8th, you're going to have a higher probability of having an issue with the math. So don't do that. So I'm going to divide that by 550 second EE negative 9. When I do that, 5.45 times 10 to the 14. Remember, we round to the, when you're doing the calculations on the calculator, please don't go past the second digits to write decimal points. So cut off at that 5. Don't go putting everything you see. That's going to be crazy. And in case you didn't know what this E letter means, it means times 10 to the 14. That's the same thing as this. E means times 10 to the. So when you see E on your calculator, it's basically telling you times 10 to the whatever power, whatever number comes up after, which is 14. We could also do this on a basic calculator, in case you're wondering. So once again, 3. Here, it's an exponent button. So the exponent is going to be 8. And we're going to divide that by 550 exponent negative 9. And you can see, once again, same value. It's just the decimal points here. You move it 14 times, you get 5.45 times to the 14. So whether it's an EXP button or an EE button, they both represent the same thing. You just tell your calculator to 10 to the whatever power, and the math becomes a lot easier when you do it that way. So I encourage you to do it that way instead of trying to do 10 to the whatever power, regardless of what calculator you have. All right, so let's continue. So we did this one. Now we're going to go to the next step, calculating energy. So the formula to calculate energy is E equals hv. H is a constant, it's this number. So I'll give this to you if I was going to have you do the calculations. If you're doing it on homework, obviously you need to, make a note of it because you're going to need it. So that's going to be that, you can see it's an extremely small number. That's the number we're going to use. V is frequency. Put all that together, and we're going to use the frequency they give us to get our energy. So how do you do that? Well, here's an example. So the energy of a blue light, you calculate a frequency of 6.3 10 to the 14, that's negative 1 for. So what am I going to do? I'm going to plug this in to this formula. So I get this. Once again, two different ways of handling it. You could do 6.626 times 6.3, get an answer. Go negative 34 plus 14 because you're multiplying, get an answer, and then make sure you have an answer in scientific notation. Or you could do it in your calculator. And for those who are like, well, how do you do it in the calculator? Let's take a look again. So I'm using the TI this time because I like to use the TI. So let me clear this up. Clear button. So 6.626, 6.626. EE button again, so second, EE, negative 34, so negative 34, not divided by, multiplied by 6.3 second, EE, 14, which is basically the same thing as this. Once again, E to negative 34 tells you 10 to negative 34. Enter. 4.17 times negative 19. Remember, E means 10 to the power. And once again, we round it to the second digit to our decimal place, basically the 100th place. And you get your answer. You're done. So you can see the math is really easy if you use the right tools. Now, for those that are uncomfortable with the whole doing everything you calculate, then you could also do it another way. Watch, I could do 6.626 times 6.3. I get 41.74. So 41.74, 41.74. So let me put it down here. Oops, sorry. So 41.74, and then you add the 2, right? So that's going to give me times 10 to the 20th power, negative 20. Because negative 34 plus 14 gives me negative 20. So now I got to do is put in scientific notation, ones to the left, remember. So 4.17 times 10, because you move the ones to the left, your exponent goes up by 1. So negative 19, and there's your joules. So now we're going to a different question. So you're calculating the energy of one photon of yellow light whose wavelength is 589 nanometers. So in order to do this, you got to kind of work your way backwards. So how am I going to solve for energy? Energy is going to equal to H times V, right? In order to do this, I need the V. This is not V. This is not the frequency. This is the wavelength. So how do I get the frequency? Well, we know that V is equal to C over lambda. So that's how we're going to operate on this. So we do C over this, which is basically 3.0 times 10 to 8 meters per second. We're going to change this into meters, right? So that's just 589. Just put the 10 to negative 9 at the end of it. Put the M, and you've already converted. You could do a T-chart to show this, but you don't really have to. So 589 times 10 to negative 9 meters. You get 5.09 times 10 to the 14. So now that I have that, I can plug that into my calculation for energy. So now I have 6.626 times 10 to negative 34 times 5.09 times 10 to the 14th. And I get my answer, which turns out to be 3.37 times negative 19. And once again, you could do it either multiplying these together and then doing the scientific notation method of adding the exponents, or you could do it in your calculator, whatever floats your boat. So that is calculations involving waves and frequency and energy.